So why scintillators in the first place? Well, the real draw of scintillators is the water equivalence for megavoltage photons and electrons. Particularly as you're going down to these really small field sizes, the perturbation of the detector itself, changing the interaction of the radiation there at the point of measurement, becomes a much more complicated issue. And so the lack of beam perturbation due to that really true water equivalence makes a huge difference in terms of your confidence in your measurements. We can make scintillators very small. They show no dose or dose rate dependencies for normal linear accelerators. We're looking into flash at the moment, but that's where we are for standard and FFF beams. We're not seeing dose or dose rate dependencies. Energy independent for all megavoltage photons and electrons, so that's also very nice. The beam quality correction factor is unity, so there really isn't a correction needed, and that's really a reflection of that water equivalence. There's a small amount of temperature dependence with this detector. It's about 0.1% per degree Celsius. So really, if you're making all of your measurements at room temperature for QA type measurements, you don't have to worry about correcting for temperature. There's also no ferromagnetic material within the fiber itself. It's all plastics. So the fiber can be used within the magnetic field of the MR-Linac. Little more detail about our scintillator. We use an organic material. The original device was the W1, had a 1 millimeter diameter and 3 millimeter long active region. With the W2, which is the more recent version, we were able to improve our optics and go down to a 1 by 1 millimeter scintillator as an optional fiber for that detector, which gives a little better resolution in terms of your volume averaging, your geometric size there. The one disadvantage of scintillators is that you do have to correct for the Cherenkov light. So this is a contaminant that is basically a stem effect sort of signal that is generated within the PMMA optical transfer fiber. It's this characteristic blue glow from a reactor coolant pool, but in this case it's generated by those high energy electrons traveling through the plastic. We employ a 2-channel chromatic correction that I'll explain on the next slide, but it's based on a publication from Matthew Guyot et al. From 2011, and that's what really enabled us to turn this into a commercial product, this nice kind of clean method for removing that Cherenkov signal. The other thing about scintillators is that they're not what the calibration lab would term an absolute dosimeter. It is something that needs to be characterized in relation to some other detectors. So really you just give it a known dose in a known configuration, and that provides the conversion factor from the measurement in terms of charge collected to the dose that's been delivered. So for this 2-channel chromatic correction, what we're doing is we're splitting up the signal into two color portions, 2 portions of the spectrum. One we call the blue region and one we're calling the green region. So our scintillator is primarily a blue scintillator, so most of the signal falls within this blue region. Cherenkov is a broad spectrum contaminant here, and so it falls across both. And what we'd have you do is a set of characterization measurements where the goal is to keep the dose to the scintillator, that tip of the fiber, keep that the same, and change the amount of optical fiber that's in the field so that this scintillation curve doesn't change, but the Cherenkov curve will be different between the two. So with that, we can look at the difference in signal for the blue channel divided by the difference in signal for the green channel and use that to create what's called a Cherenkov light ratio, which is used as a correction factor for later measurements then. So the scintillator signal from measurements, once you've done your characterization, is this blue signal minus the green times the Cherenkov light ratio, which gives you that contribution of Cherenkov within the blue spectrum. If you do a dose calibration, you would give a known dose in a reference field. That just becomes a scaling factor multiplied by this equation. We have 2 methods that are available for the W2 For that CLR characterization, this is the one, this little blue jig is the one that comes with the system automatically. It has a vertical post that would be held within your water tank. The minimum fiber configuration, which is that small amount of optical fiber in the field, would have this coming straight out of the jig. And then what we call the maximum fiber configuration has the fiber wraparound. So this fits within a 10 by 10 field if you're using a linear accelerator. It can also be used within a circular 6-centimeter cone if you're using CyberKnife. We also have a slab phantom version that was initially developed for the W1, but it's available with the W2 as an option. And that's just a larger phantom, solid piece of plastic with a channel milled out for the minimum fiber configuration and a larger curve for the maximum fiber, and markings for 10 by 10 if you're doing your calibration. So with the W1, that original version, that's been out since 2014. It's kind of hard to believe it's been 8 years, but it's been out that long. It has a 1 by 3 millimeter active scintillator at the end of that fiber. And there are quite a few publications available about the W1, but the most notable is that joint publication from the AAPM and the IAEA on small field dosimetry, that's TRS 483, which lists the W1 with that KQ of 1 in every single table that it shows up in. And that really is the only detector within that publication that has really no correction, no effect based on that decreasing field size and the change in the spectrum. It was, however, just a single point measurement system, and it required a 2-channel electrometer like our Supermax electrometer in order to perform that Cherenkov subtraction. So once we had a little experience with the scintillator, we had gone that far. The next request from the people, from users, from customers, really were twofold. One, I'd like to use it with my water tank, and 2, I'd like to have that scintillator be uniform size so that it doesn't matter which orientation I use it in. And so that's what brought about the development of the W2. It has a dedicated optics and electronics unit called the Max SD. It has user replaceable fibers so that you can exchange between a 1 by 1 or a 1 by 3 millimeter fiber, or a long fiber for use with an MR Linac. So if you buy the system, you get both the 1 by 1 millimeter scintillator and the 1 by 3. There are a couple reasons for this. One is that there are so many publications about the W1 that we wanted to provide you with that physical link back to those publications to say I'm measuring with the identical fiber, the same fiber that was used, materials, construction, everything is the same as those W1 presentations. Or publications, sorry, but then also have that 1 by 1 for the finer resolution of the ultra small fields where volume averaging over a 3 millimeter length of scintillator is not acceptable. The other advantage of having both is that for water tank scanning, this is a low signal device, and therefore there is some noise with the scanning. So you have to scan slowly in order to get some good data. But if you use the 1 by 3 in those fields that you feel it's acceptable to use that, you get 3 times the signal, and therefore your noise, signal to noise ratio is better. You can do point measurements as well as your Cherenkov correction directly with the Max SD interface. But then also, as I mentioned, you can use it with your water tank. And what happens there is the Max SD is really just a pass-through to process that signal and remove the Cherenkov, and then send the corrected signal on to your water tank. So this is what that looks like. We provide an adapter sleeve for the W2 so that it can be held with any standard scanning chamber water tank holder, or water tank scanning chamber holder, I guess would be a better way to say that. The fiber then is attached to the back of the Max SD so it can read in that optical signal, perform the Cherenkov correction, and convert that to an analog output, a current that can be read in by the input channel for your water tank electrometer. I discussed the CLR jig here, but this is, or previously, but this shows that minimum fiber, maximum fiber configuration. So from the standpoint of the water tank, this detector acts like a diode. You don't apply bias to it, but when it's irradiated, there's a current that's generated that can be read by your water tank. An example of this here is from a publication from Paulina Galavis in 2019 when the W2 was first coming out. She compared the scanning points with the W2 with radiochromic film. This is a 1 by 1 centimeter field and got excellent agreement there. They also verified that there wasn't any dose rate dependence seen or dose dependence. And another interesting publication from Jesse Snyder, Richard Popple's group at the University of Alabama at Birmingham, also 2019, where they looked at patient-specific plans with patient targets down to 3 millimeter diameter target, which was the smallest one they looked at, and got, again, excellent agreement between the W2 and films for a high number of patient plans. So that's what I had for you today. Please feel free to ask me your questions. If you want more information, you can visit our website. I'm always happy to talk about the W2 if you think of anything that you'd like to ask about.